strategies for determining convergence or divergence of an infinite series. Alright, so determining convergence or divergence of an infinite series can be quite the task. So in order to make the process a little more systematic, I want you to run through the following steps in your mind when you approach any particular problem. So first, you need to ask yourself, does it look like, or can it be rewritten to look like, first, a geometric series? So of the form AR to the n or AR to the n minus 1, depending on the starting index, at which point we apply the geometric series test. If it's not geometric, does it look like a p-series, or can it be rewritten to look like a p-series? So the sum of n equals 1 to infinity of 1 over n to the p, where p, remember, has to be a positive real number. And if that's true, then we can apply the p-series test. Or does it look like a telescoping series? So telescoping series often look like the sum of the difference of two different functions, where you are likely to see the same number over one function minus the same number over a different function. Or can it be rewritten to look like a difference using partial fraction decomposition? And if it is a telescoping series, then subsequent terms are going to cancel, leaving any remaining terms to be the sum of the convergent sequence. So if none of these work out, then we try the nth term test. So that says, given an infinite series a sub n, if the limit as n approaches infinity of a sub n is not 0, then we can just stop and say the series diverges. But if the limit of the general term as n goes to infinity is 0, the infinite series may or may not converge. More work needs to be done. So the next step is to decide if we have all positive term or alternating term series. Now, if positive term series, we can try any of the following tests. So the direct comparison test. To use this test, these often have a constant in the numerator of the general term. And we try to compare this to a p-series or a geometric series. For the limit comparison test, we try to use this when the general term looks like f of n over g of n. So often a polynomial divided by a polynomial is your indicator to use the limit comparison test. And we compare to a p-series with p chosen to be the difference between the degree of the numerator and the degree of the denominator. We know to use the ratio test when you see factorials. So if you see something like n factorial or general exponentials like 5 to the n in the general term, that tends to be an indicator that I want to use the ratio test. For the root test, we try this when you see a general term, let's just say term, raised to the nth power. And then if none of these work out, then we use the integral test, which we'll cover a little later in the year. And we're going to do this one last anyway, if it looks like it will integrate nicely. If it was an alternating term series, then we're going to try the alternating series test. And we try this when we see negative 1 to the n, negative 1 to the n plus 1, or cosine pi n in the general term. Or, of course, we can try the ratio or root test that we described above. Okay, so now let's try to put that list into use. So here are some infinite series, and we want to figure out what test we should use to determine convergence or divergence. So I have the sum of n equals 1 to infinity of n squared minus 1 over n squared plus n. Alright, so here, this doesn't look like a special test like geometric or p-series or telescoping. So at this point, I can try the nth term test. So again, we don't necessarily have to try them all by hand. We can try them mentally to roll through this process. So hopefully you can see that the nth term test of this general term is going to give us 1. So once we decide the nth term test is actually going to help us show divergence, we should write it down. So the limit as n approaches infinity of n squared minus 1 over n squared plus n is going to equal 1, which is not 0. So by the nth term test, we have that this series diverges. Looking at number 2, I have the sum of n equals 1 to infinity of n minus 1 over n squared plus n. So again, not geometric, not a p-series, not telescoping. So we would try the nth term test. We can go ahead and look at the general term to decide if the nth term test would help us. And this general term here would be going to 0 because the degree in the denominator is bigger than that in the numerator. So the nth term test really wouldn't tell us anything. So now this is going to be a positive term series once I get past a particular number. So when I plug in 1, I'm going to get 1 minus 1, which gives me 0 over 1 plus 1. So 0 over 2 is 0. But past a particular point, past 1 in particular, so starting with 2 and so on, I will have a positive term series. So let's run through our positive term series test. For the direct comparison test, I would want just a single constant in the numerator, and I don't have that. But for the limit comparison test, I want what looks like a rational function, which is exactly what this is. So here, I want to use the limit comparison test, and the series I'm going to compare this to is 1 over n, because this is n to the 1, this is n squared, so the difference in those exponents is 1. So I'm going to compare this thing to 1 over n. So I'm going to set up my limit for the limit comparison test. The limit as n approaches infinity of n minus 1 over n squared plus n. So technically it's this divided by the term I'm going to compare it to. So the term I'm going to compare it to is 1 over n. So instead of 1 over n, I'm going to multiply by n over 1. So now this becomes the limit as n approaches infinity of n squared minus n over n squared plus n. And as n approaches infinity, this thing goes to 1. And now we have to remember the conclusion of this test. The limit comparison test says if this is positive and finite, which it is, then these two series behave the same way. So positive and finite. So since the sum of 1 over n, which I compared it to, diverges, the original series, n minus 1 over n squared plus n, must also diverge. And now looking at this last one, I have the sum of n equals 1 to infinity of 1 over n squared plus n. So not geometric, not p-series, not telescoping. If I look at the nth term test, the nth terms, as n goes to infinity, will go to 0, because the highest power on the bottom is 2. So now we have to run through our positive series test, because these are all going to be positive terms in this series. So direct comparison test, usually we're going to have just a constant in the numerator. So this one is a good candidate for the direct comparison test. And I'm going to compare it directly to 1 over n squared. So the sum of n equals 1 to infinity of 1 over n squared plus n, I want to compare this to n equals 1 to infinity of the p-series 1 over n squared, which by the p-series test, since 2 is greater than 1, this series on the right converges. So if this series converges, then I want this one to be less than or equal to a series that I already know converges, because if I have a smaller series, it must also converge. So in other words, I need 1 over n squared plus n. So I want this to happen. Let's make that clear. So I need 1 over n squared plus n to be less than or equal to 1 over n squared. So if this is true, then what I need is for the denominator over here, n squared plus n, to be a bigger number. So I need n squared plus n, questioning this, to be bigger than or equal to n squared. Well, n squared plus n, if I have n squared on both sides, but on the left side I'm adding n, then this side is going to be bigger than the right side. So that means this inequality will hold true. So what I wanted to happen is actually happening. So this inequality holds true. So by the direct comparison test, this series converges. Alright, so for this next example, we have the sum of n equals 1 to infinity of negative 1 to the n minus 1 times n minus 1 over n squared plus n. So hopefully this one screams out that we should use the alternating series test because of the negative 1 to the n minus 1 part. So is this alternating? Absolutely, because I have the negative 1 to the n minus 1. Number 2, we're asking ourselves whether this general term gives us individual terms that are decreasing in size. So here, if I write out the list of terms, if I plug in a 1 first, I'm going to get 0. If I plug in a 2, I'm going to get 1 over 2 squared is 4 plus 2 is 6. If I plug in a 3, 3 minus 1 is going to give me 2 over 3 squared plus n, so that's 9 plus 3, so I'm going to get out 12. So right now, between these couple, it doesn't look very good, so let's keep going and see if it works, because it only has to work past a certain point. So now, if I plug in a 4, 4 minus 1 gives me a 3, over 4 squared is 16 plus 4 is 20. So that looks good, and let's just try one more. So 5 minus 1 is going to give me a 4 over 5 squared. So that's going to give me 25 plus 5 gives me 30. So yes, at first, the first couple terms didn't work out, right? Because we wanted them to get smaller. So 1/6 is not smaller than 0, and then 2 over 12 is 1/6. So that's less than or equal to at least. And remember, we're trying to show a sub n plus 1 is less than or equal to a sub n. But once we started moving further, we can see that these are getting smaller and smaller. So 3 out of 20 is smaller than 1 over 6, and then 4 over 30 is smaller than 3 over 20. So these are getting smaller, so this portion does hold true. And then the third part, does the limit of the general term go to 0? So n minus 1 over n squared plus n. It absolutely does go to 0, so by the alternating series test, we can say that the series converges. Alright, so now let's take a look at number 5. I have the sum of n equals 1 to infinity of negative 3 to the n plus 1 over 2 to the 3n. Alright, so we want to ask ourselves whether or not this looks geometric. And hopefully you might be thinking that, yes, it sort of does if I manipulate it a little bit. So I'm going to go ahead and pull number 5 off to the side. I have the sum of n equals 1 to infinity of negative 3 to the n plus 1 over 2 times 3 to the n. Alright, so since my starting index is 1, I'm actually going to need an n minus 1 here. So let's work on the numerator first. This is n equals 1 to infinity. In the numerator, I'd have to pull out 2 copies of negative 3. So negative 3 squared, and then I'd be left with a negative 3 to the n minus 1. So if you need convincing, remind yourself that since these have the same base, I would add these exponents together, and 2 plus n minus 1, the 2 and the minus 1 would give me the plus 1. So that's what we have going on the top. And on the bottom, alright, I have 2 to the 3n. So this is really the same as 2 cubed to the n, because my properties of exponents say I can multiply these. So the bottom is really 8 to the n. And I need there to be an n minus 1, so I'm going to have to pull out an 8. So let's keep going with this. This is n equals 1. Well, 3 squared is 9. So the top is like 9 times negative 3 to the n minus 1. And on the bottom, I'm going to pull out 1 copy of 8, so that I'm left with 8 to the n minus 1. Alright, so now this is the sum of n equals 1 to infinity of 9 over 8 times negative 3 over 8 to the n minus 1. So let me make a little bit of space here. So now we can hopefully see that this is clearly geometric, and because the absolute value of negative 3 over 8 is less than 1, by the geometric series test, this converges. And it converges to a, so 9 over 8, over 1 minus my r value. So my r value is negative 3 over 8. So I would include the negative here. So if we wanted to simplify this, this would be a plus. 1 is 8 over 8. So this is 9 over 8 over, this is 8 over 8. So this is 11 over 8. So if I multiply by the reciprocal, this is 8 over 11. So the 8's cancel. My final answer is 9 over 11. So not only do I know that this series converges, I know what it converges to because it was geometric. So that took up a lot of space, but we can go ahead and do the last one with not too much work. Here I have the sum of n equals 1 to infinity of the quantity 3n over 1 plus 8n to the nth power. So since I have a whole term being raised to the nth power, I should think to use the root test. So that tells me that I can do the limit as n approaches infinity of the nth root, let's make a giant nth root, of the absolute value of the quantity 3n over 1 plus 8n to the nth underneath the nth root. So now I'm going to rewrite the nth root and remove the absolute value bars because this is going to be positive. So this is 3n over 1 plus 8n to the n, all raised to the 1 over n. So when I see that nth root up there, or to the power of n, I think the root test so I can get rid of it with an nth root, because n times 1 over n cancels. So now I'm just doing the limit as n approaches infinity of 3n over 1 plus 8n, and since these degrees match, my answer is 3 over 8. And remember, the root test has the same conclusions as the ratio test. Since this is less than 1, we know that the original series converges by the root test. So this is really a matter of practice and really just breaking down and thinking about what the general term looks like and what are the different tests that I have, and really sort of formulating this list in your head so that it makes it a little bit more organized in the way that you apply all of the different tests that we have.